version of notes. I'm trying to get through this pretty quickly here. You probably can tell, not at school. I'm in my basement again. So, hope you enjoy all the decorations that you might see floating about. Section 6.4, parallel lines and proportional parts. Some of the problems that we've done over the last couple of days where I've told you either you get it right or you get lucky, kind of shows why you were getting lucky with those problems today. Basically, just a couple theorems, a couple of little things, some examples, and pretty good to go. We'll get into stuff as we get back in class. First theorem, triangle proportions theorem. If a line is parallel to one side of a triangle and intersects the other two sides, then it separates the sides proportionally. Really hope this is showing up on the notes pretty well. Daughter's markers. So basically you can see here in green, I've got a triangle set up, triangle ABC, with the segment kind of coming through here, segment DE. You can tell by the little arrows that segment DE is parallel to my base here, BC. Does it always have to be parallel to the base? No. I could have a segment going this way, parallel to AB, or I could have a segment going this way, which would be parallel to segment AC. You just have to have a line going through the triangle that's parallel to one of the sides. If that's the case, then what's happening is this new segment or new line is dividing the other two sides proportionally, meaning if I compare segment AD to AE, that should be the same as comparing segment DB to EC. So I'm looking at AD, AE, DB, EC, or I could compare segment AD to the bottom portion here, DB, and set that equal to segment AE compared to the bottom portion of the side over here, EC. Either way, notice here, what we're cross multiplying ends up being the same thing both times. So we'll show you an example of that a little bit later on. The converse of that theorem is also true. So basically, the converse says, hey, if you have a line that separates the sides proportionally, then that segment or line is parallel to one of the sides. So basically saying, hey, if I didn't know that those were parallel, but I knew that both or one of these proportions was true, and if one's true, the other one's going to be true as well, then that means that these two segments would have to be parallel to one another. So it just kind of works both ways. If they're parallel, they cut proportionally. If they cut proportionally, then you're going to have some parallel segments within that triangle. So environment. Couple of quick corollaries. Corollary 6.1. If I have three parallel lines that intersect two transversals, so here my green lines are the parallel lines, the black lines are the transversals, then those parallel lines divide the transversals proportionally. So basically what we're saying is this. Segment AB compared to segment BC, the top part of the transversal compared to this bottom segment, that would be the same thing as comparing the top segment of this one to the bottom segment of that transversal, FE to ED. Alright? So I can compare them top to bottom, or I can go left to right, left to right. And you can see that over here in the proportions that I've kind of laid out there for you. And again, I'll show you some concrete examples of what we're talking about here in a second. And the other corollary that we're going to talk about, very similar, again, three parallel lines, three parallel lines, except now we start to have multiple transversals, more than two transversals, okay? If three or more parallel lines cut off congruent segments, that's the key here. Now we're not talking about the segments being proportional to each other. We're talking about the segments being the exact same measurement. So if they cut off congruent segments on one transversal, then what happens is they actually cut off congruent segments on every single transversal. So if I know that segment AB is congruent to segment BC, then for every other transversal that's going to intersect those three parallel lines, we're always going to have congruent segments. Not congruent to the original pair of segments, but congruent to each other. Here, this segment FE would be congruent to segment ED. Here, segment GH would be congruent to segment HI. If I extend these out and add more transversals, I'm going to have more pairs of congruent segments. So that's pretty much the bulk of the notes in terms of theorems and other little sweet tidbits of mathematical knowledge. If you want to go back and jot that stuff down real quick, feel free. We'll get into some examples here right about now. So if you want, give yourself some space in your notes. Notice I haven't worked anything out just yet. I'm hoping that this will work out okay where we can work them out as we go. If you want to pause and jot down the examples, hopefully everything's showing up well in the video and stuff's not falling down. So, alright, so on the first example, we've got a triangle here, triangle ABC. So you've got some measurements here. We've got a segment coming through here, DE. The question is this segment DE parallel to the base BC? Again, does it always have to be segment base, segment base? No. I can sit there and switch it up. You'll see here in a second I do. But I've got some measurements here. 3, and then 6, 4, and then 8. So if I want to show that this segment is parallel to this base, then I should be able to set up a proportion with these different measurements. Essentially looking something like this. If I compare 3 to 6, that should be the same thing as 4 to 8. Now clearly, pretty simple numbers here. I should be able to tell that, hey, both those reduced down to 1/2. I'm going to be good. And so I could do that. I could sit there and say, hey, you know what? This is 1/2. This is 1/2. And so, yes, I know my segments are parallel to each other. Another way to go about it, go ahead and do the cross multiplication. 3 times 8, 24. 6 times 4, 24. And since my cross products are the same, I know that, yes, my segments are proportional, which means that those two segments, DE and BC, are going to be parallel. Alright? In our second example here, you see that we already have a set of parallel segments, BD and AE. This time, though, we don't have full-blown actual lengths of segments. Here we've got x plus 2 for AB. Right below that we've got 4. Down here for CD we've got 6. And for DE we've got 2x minus 1. 3 things we want to figure out. Well, 4. The value of x, and then the lengths of these 3 segments, AB, DE, and segment CE. So again, because I've got a pair of parallel segments here, I know that that tells me, hey, these segments are proportional, and so I should be able to set up a proportion to show that the corresponding segments are in fact going to be equivalent. So, again, multiple ways you can go about it. I'm going to kind of stick with, if I start out with x plus 2 and compare that to 4, so I'm sticking with one side of my triangle. So now I want to compare that to this side of my triangle. So that's going to be 2x minus 1 over 6. So the two segments here closest to point C correspond with each other. The other two segments, x plus 2 and 2x minus 1, those correspond with each other. Cross multiply, distribute, solve, and you're good. So here I'm going to get 6x plus 12 equals 8x minus 4. Get my x's to one side, I'm going to subtract 6x. I'm also going to add 4 here and here. So 16 equals 2x, which means that x equals 8. So there's my value of x. Segment AB is x plus 2, so that's going to be 10. DE, 2x minus 1, so 2 times 8 is 16. 16 minus 1 is 15, which means that segment CE, if I add those up, I got 6, I got 15, that's going to be 21. Alright? So, again, as you go through, if you have questions or if you're not catching on everything that we're talking about, rewind, go back and take a look at the examples again. Listen to the explanations. So, see if that helps out. The last one we want to take a look at, down here at the bottom, we've got the parallel lines. Three different parallel lines. We've got some transversals coming through. Notice no congruence markings. Alright? If we were going to set anything equal to each other, we would see congruence markings, the little tick marks, the double tick marks that we've seen before. So since we don't see that, we should be thinking proportions. Alright? So I know that segment AB and BC are proportional to each other. I know that FE and ED are proportional to each other. So again, want to determine the value of x, find the lengths of a couple segments. I'm going to set this one up a little differently. Here I've been comparing the same size to each other here. I'm going to go left to right instead of top, bottom. So here I'm going to go x plus 2 to 5 equals 3x minus 4 to 9. Go back to the blue marker. So when I distribute, I get 9x plus 18 equals 15x minus 20. If I add the 20 over, that's going to be 38. If I subtract the 9x, that's going to be 6x. So when I divide, x is going to equal, that's going to go 6, 2 left over. X is going to be 6 1/3. So that means that segment AB, x plus 2, is 8 1/3. That means that segment BC is going to be, let me see, 3 times 6 1/3 minus 4. So that's 18, that's 19, that's going to be a total of 15. And AC, so add those two together. That's going to be 23 1/3. Just double check our math real quick to make sure we're good there. 9x and 18, 15x and 20, 38, 6 1/3, 8 1/3, 18, 19, 15. Yeah, looks good. So, if you got any questions, rewind. We'll go over more of this stuff when we come into class. There's some other parts of this section we're going to talk about, so we'll see you tomorrow. Have a great day.